Hello, good morning. My name is Li Liyuan, and I come from the Visual Intelligence Department from Esquire. So my topic is on the AFD, means learning from demonstration. So explore the probabilistic logic in programming for visual understanding, reasoning, and to try to learn the task efficiently with very few training. Okay, so in the previous talk, there are many emphasized. So for our project, we targeted for the human working together with cobalt. So what is the natural and the flexible collaboration? So working together, and maybe also the human may instructing the robot and teach the robot to do some new tasks very effective. Yeah. So what the challenge is that if we simply use the extreme method, yeah, so you may have to collect a very large data set to training. But in the working industry environment, you cannot predict how the industry was objects and also operation of objects. So what is the combination of this? Maybe also is a new one. So it's maybe difficult to collect the whole data set to training in advance. Yeah. So we target actually we have the probabilistic reasoning that we associate the concept and also the observation detection, and then to try to make a very quick to understanding, also intelligent understanding. Okay, so how to do this? First requirement is that so you want to deploy the cobalt. It's very quickly and easy to the new tasks, and maybe you have a change, great change. So in that way, we have first to that robot to the all the related objects. This can be trained in offline, so all the related objects in the industry tasks. And then maybe for the new task, it's just only training one times. That's a human perform one task. So like the human to human teaching, that is expert to teach the new stuff. And then the robot or intelligent system how safely generate the task representation, task graphic. And this task can pass to a robot. Robot can perform the task. So that means the almost no need of the robot expert to perform the handcraft X program. So how to do this? We have two key technology. One is the localization. One is the manufacturing. So localization is you have to do all the related objects. You know what is this? What is the pose and what is the location of the components or whatever. And then for the correct assembly instruction, which party is in which location. That is very important. For this, maybe we'll no time to teach too much. So maybe just teach one time. Then robot have to remember this. The second is manipulation. After this, you will have to understanding the human operation, whether for how to pick what object and place object in after this. And then so this we also use associated action with object. Yeah, so leading to training to all the complete combination of the operation and objects. Okay, so this is the general diagram of our target and also our system. So our target is just about human, just perform this task one times. This. Then our robot post can detect the object and the human and hand, whatever, and this, tracking this. And after the human performed, completed the task, we want to generate the task graphic. The task graphic has a human operation and what object is operating, what is involved and what is placed. What is it? Even you can see here is important that this shaft should be placed in this hole. If this hole is not the correct assembly. So how to do this with a hybrid AI method. And first, we use the deep learning to detect object and hands and pose and gesture. And then we use just a simple visual memory, visual working memory to tracking the human hand object state, statical or moved by hand, and where is from the start point and the end point and position. And after this, we do the probabilistic logic reasoning based on this detection. First, we had a located object based on we called the LCG, local contextual graphic, data graphic. Data graphic can look object and there is component associations. And also the hand movement, the move to object things in the real world working condition, there be class object on the table, any other components. So the which object, hand which object, and pick which object, and then where to place. This is the most related to the task we build this. So once we generate this graphic, we can transform to robot, and robot can perform this. So that's very easy. That takes one time, and then cobalt to perform the new task. Yeah. So first, for the localization, we proposed a new representation. We called the local context graphic. Right. For each object and its components, for we have the first each kind of loads, and then for the fixed assembly relations. So for each two objects, we have the relations. It's the object level, related size, and related distance. And therefore, it is three objects. We have the triangle relation. The triangle based on their location, orientation, the distance, relative distance. So you can see this scale. We can how robot place what object with location. And this is a robot place operate on the object. And this is a hand. A hand we can just take that this is the root tip. This is the front tip. We can take this and then build the relation of this related size and distance, and then you can if we compute the detection, just detection these tips. This is detect future object. A visual object, and then based on this relation, we can calculate this is the handler, and then where is the handler by the robot. And this is very important for robot operation. Okay, so based on the LCG local context, so just use one object purpose. You just when yeah, you may just one example, and then it's located location just teach one times. And robot can just show the robot. The robot can automatically learn this LCG. LCG. Once the LCG in the application, it's a new import. Is frame import has a detect computer vision. The deep learning detect object. Then for each based on the LCG, we deliver all the hypotheses. So this is the detections of objects, and this is the object priority of a lot, and also the pair, and also tree. And then based on the LCG, we can deliver all the hypotheses, related hypotheses. And this hypothesis to this engine, and then you have a task, it's a localization or detecting the correct assembly, whatever, and then this become the role. Into this, we perform the probability logical reasoning to a task to locate the object, and then you can teach out here. This is base, and this have the components, and we have the assembly task that put this shaft to one of these components. Okay, this is the mathematical formulation of how to produce the hypothesis from the loss, hypothesis from the agent, based on this SDG representation. I will skip this detail. Okay, this is based on the hypothesis. We can produce. This is from the formulation of neural symbolical reasoning formulation. That means if we have all the detection names, object, and then it's SDG, we could try to find out the related object sets. To meet to achieve the high probability of this hypothesis from the LCG, from the local contextual graph. So we have if we have all have the high probability, we can locate the object. If some is missing, this is not correct configuration. For example, probably we show if for object we can to perform the localization. Another task as well, we can see if we have the correct assembly. So in the industry case, we maybe have just the correct assembly. This is example of three objects is the correct assembly. But you don't know the unfaired configuration. There are many ways to have faired assembly. But just teaching of this, just a few examples, and based on our probability reasoning, and then if we have found this one, or this distance is too large based on the local contextual graphic. So we can say this two is the correct assembly, but this is not the correct assembly. So that can always have successful assembly, a lot of successful assembly. Yeah. Okay. After the localization, okay, was understanding the human hand movement and also the action. For to do this, we have to from the basic detection of from the deep learning. We have to use the tracking of the hand. The first hand movement, that means hand move to the object, hold object, move away, move together. This is the movement. And also based on movement, have the atomic action. Pick up is a group of the hand moving to object, hold object, and moving together away. And then after this atomic action, we have to deliver automatically generating the task representation, task graphic. How to do this? First, we have defined 4 roles to describe. This is 4 roles describe the hand movement. Okay, yeah. So first example for what I did that. So for the hand eye move to object J, we have just a rule, not the training for many training sample sequence. Just a way. So that's if the hand move to object J, that means the distance from the hand eye to J to be reduced, constantly reduced. And then the orientation from the hand movement to the hand direction to the object, the target object should be the same, all same direction. So if the hand hold object, I mean, hand is stable and hand touch the object, and also the distance keep constant. So based on this movement, and based on that, you can detect the automatic action, like the pick up hand eye, pick up object. That means move the hand move to eye, move object, hold object, and move again altogether. So that means just the basic rule isn't needed to training of the sequence. Our machine can understanding these actions. Yeah. So this is all details. We additional rules to make the adaptive to the different hand movement. Hand movement very fast and very slow, whatever. So I have to adapt to this. So needed to collect large data for our variation to training, but just is the different rules. You can do this. Okay, this is the mathematical how to finally select the task to form the task graph based on the recognized the atomic actions. So also we have the developer for the adaptation to the occlusion. So we find if you have the schooling, you hold the schooling, so school is very small, your hand moves close, you cannot apply this. But this we detect if the hand close to the close to the school, and then hand move away is no school in the original place. That means hand pick the school and move away, but they cannot see the school. Okay, so previously I shown the video. We have shown the example, which has just a human show the when kind just the perform 1 times, and you can robot can do this and then to perform the task. So another application is this: once we just 1 times, we can then the task graphic, and then if there is a task graphic and if you shoot with available camera, and then it can also use to monitor the new stuff for the operation. For operation, and this kind of tracking the human address. If there somewhere have not correct correct operation, correct installation, and we can give a line to even to guide the people to the correct operation. Yeah. So this is just very quickly training, and then deploy the flexible new task, and then if we like to maybe next task. Also, currently we focus the task graphics just to show that the operation and the object. And yesterday, Rina has suggested in the industry environment, we also have the tools. For each object, when install object, you have special tools. So as each the operation, object, and tools should be associated together in this graphic. So it's more close to the real world operation. Yeah, so in graphic, just the compression. So if we say end learning, you have to collect the larger data, and also needed to hand programming. But this we just the cost cost is low, just the training the image recognition, object recognition, and then another is just to teaching with 1 times of the operation. But they may need the domain knowledge to design the probabilistic logic for perform this. Okay, yeah. So that's my question. Any question? Oh, okay. Thank you.
Thank you, Dr. Li. So we'll be doing the questions at once during a panel discussion. So keep your questions for then. Thank you.